and all that stuff. Make sure we officially cover it here together. Last time we talked about bonding, we talked about the three different types of bonding, really. There's ionic bonding, which is always between a metal and a non-metal. And remember, in that type of bonding, we have a transfer of electrons. So the metal becomes positively charged and a cation. The negatively charged non-metal there becomes an anion. And in an ionic compound, it is that attraction, as we talked about, between those two things that hold that together. Again, no sharing of electrons happening. And that's different than covalent bonding, which is really kind of two types of covalent bonding. But regardless, either type of covalent bonding involves nonmetals. And with covalent bonding, it's usually two nonmetals. And we got some sharing of electrons here. And that sharing could be equally, which means it is a non-polar covalent bond. The sharing could be unequally, which means it's a polar covalent bond. And really what determines sort of the sharing of those electrons is the electronegativity values. So we could use electronegativity values of each of the elements involved in a bond to determine whether or not really the electrons will be shared equally or they'll be shared unequally, or even if they'll be transferred. Although, as we talked about with ionic compounds, you don't really need the electronegativity values as long as you see it's a metal, non-metal. It should be an ionic bond. But we definitely could use it for polar and non-polar bonds. We also don't necessarily even need the values, especially if we're comparing things in the same row or the same group on the periodic table. We could just use the general trend in electronegativity to help you decide whether or not it's going to be polar or non-polar. We got into drawing Lewis structures for covalent compounds and a couple of important steps, right? You want to count up the total number of valence electrons. You want to have a logical arrangement of the atoms. Usually the least electronegative is in the center. So the least electronegative atom usually is in the center. We don't usually have hydrogen in the center because it should only have 2 electrons. And we don't usually have fluorine in the center because it is the most electronegative. You then want to basically make one single bond from the central atom to the outside atoms. Remember that basically each line is 2 electrons. So that's going to obviously use up a certain number of electrons for you. You'll have a number of electrons that are left. Those go on the outside atoms first, and pairs of electrons on the outside atoms until filled. Then to the center atom. Thank you. Also in pairs, if you should still have leftover electrons basically happening. At that point, you probably should be used up all your electrons with the central atom. You then want to make sure everybody meets the octet rule. If not, that really is where you should double or triple bond to try to fix anything that has not met the octet rule. A reminder that you should double bond or triple bond usually out of the box, and you kind of want to exhaust all your double bond opportunities and before you roll into a triple bond in most cases. At that point, you should have hopefully the correct structure there. Any questions on any of that stuff there? All right, so I think we did a couple there at the end last time. I think we did it NO3 minus, I think we did. I'm not mistaken. So I want you to take a couple minutes and draw these Lewis structures here and see what you come up with. Let me change a couple, maybe let's do, we'll do carbonate. Let's do this one as SO2. Okay, let's take a look, see how you're doing. So we'll start with the first one. Remember, really, one of the important things to start with is the total number of valence electrons. So carbon is group 4, so it has 4. The valence electrons equals the group number, right? So that's 4. There are 3 carbons, each at 6 with an extra plus. And we do have a -2, so negative charge means we gained electrons, which means we do need to add those into our total count so we have the right amount. That's like 18, 20, 24, I think. In this case, carbon and oxygen are in the same row, which means carbon is less electronegative. And in most cases, the one element's in the center. And that would be the case here. We're going to do a single bond from the center to all the outside electron atoms. That is 6 electrons total. That leaves me about 18 more to go. That's going to go on the outside in pairs. So 2, 4, 6, 8, 10, 12, 14, 16, and 18. At this point, I've now put up all 24 of my electrons. We want to make sure everybody is good. And in this case, carbon in the center is not good. It has only 6 electrons. So we do want to make a double bond. And in this case, all the oxygens are equivalent to each other. So you can make it at any one you want. A reminder, though, that when we do make the double bond, we are actually taking a pair of electrons in to do so. And when you do that, you'll end up with something that looks like this, perhaps. A little bracket around it and a -2 makes it all pretty. You could have also double bonded to the left-hand side there, which would have looked something like this. And you could have double bonded to the right-hand side, which would have looked something like this. All 3 of these structures, once again, are what are referred to as resonance structures of each other. They are all sort of equivalent structures, and that is because, again, here, those double bond electrons are sometimes referred to as being delocalized, which means it can at some point be hanging out over here at this oxygen, be up there at that oxygen, be over there at that oxygen. So they're sort of moving around. So you could draw any one of the 3 structures would have been sufficient. If you were just asked to draw a Lewis structure, if you were asked to draw all the resonance structures, you should lay up all 3 of them. And again, they're usually use this arrow between them to indicate that they are resonance structures. Any questions on that there? Usually what happens in a situation like this where you have really more than one option as to where you could perhaps make that double bond so you could draw an equivalent type of structure that occurs. All right, let's continue on then to SH2, I think we got next here. So that's going to be 6 for the sulfur, 2 times 1 for the hydrogen. So that is 8 valence electrons. Sulfur has to be in the middle as hydrogen cannot. So we're going to do a line to each of them that has 4 electrons that have been used. We have 4 more to go. Again, the hydrogen cannot take any more. So at this point, we do go to the center here, and we would put our electrons as dots there. And now we have 8 electrons, and everybody's good, including hydrogen that has just 2 electrons. Any questions on that one there? Rolling to NH4 plus, I think was next. We have 5 plus 4 times 1. In this case, we have a plus, which means we need to subtract 1 from the total. That gives us 8 valence electrons again in this case. Nitrogen in the center, hydrogen's around. And a single bond to each of those hydrogens, and that will do it, I think. That's a bad hydrogen there. And we'll put a little plus on the outside there, and we should be good on that one. Then we have N2 and SO2. So N2 and SO2 left. All right. So N2 here is going to be 5 times 2, basically, or the opposite way, I guess, is 10 valence electrons. In this case, there really is no central atom, so we just kind of line them up next to each other. And we can follow the same process here. A single bond is 2 electrons. We still have 8 to go, so 2, 4, 6, and 8 in this case. This case, the nitrogen on the right is good, but the one on the left is not so good. So we're going to bring a pair of electrons in to make a double bond. And in this case, we end up with something like this. Did it fix the nitrogen on the left here? It did not. We are now up to 6. It got a little better. So we do need to make a triple bond. In this case, works the same way. We're going to take a pair of electrons and bring them in to make the triple bond. And now at this point, we will have a triple bond on each of those. And now we do have 8 electrons at each, and they are both happy still, just a total of 10 electrons at this point. Any questions on that one there? And lastly here, we got sulfur, which is 6, and 2 times 6 for the oxygen, 18 valence electrons. Once again, here, sulfur and oxygen in the same group. Sulfur is lower, which means it's less electronegative, should be in the center. Going to do a single bond there. That's 4 electrons on the outside, 2, 4, 6, 8, 10, 12. At this point, that's a total of 16 electrons that have been placed. I still got 2 more to go, and they do go on the center as dots in this case. That's how they get there, and they should be there, by the way. At this point, we look, and we've now distributed 18 electrons. And at this point, the sulfur is not good, so we can't double bond. Either oxygen will work here. So we're going to take a pair of electrons in to do so, and that's going to get you the double bonded oxygen on that side, which you could also draw a resonance structure by double bonding the oxygen to the other side, which would look something like this. Any questions on that? So that one should have the dots on the central atom. Should not be double bonded on both sides with no dots. Yes, so it should actually have the dots on the central atom for this particular one. Any questions on, again, how to draw Lewis structures? If you follow those steps that we just did and sort of talked about, you should really end up with a pretty good structure, that you draw. May not be the perfect one every time, but pretty close, should be pretty good. All right, then let us not talk about that since we just drew it. There we go. So obviously we talked about resonance structures. We're going to talk about a little bit more here in just a second, but we also want to talk about bond length. Bond length is the distance between obviously the 2 atoms that are in the bond sharing electrons. You don't have to memorize any of these numbers, but if we look at a carbon-carbon single bond to double bond to triple bond, what we see is the length goes from 154 to 133 to 120 to the triple bond. Same sort of pattern happens with the carbon-nitrogen single, double, and triple bond. Goes from 143 to 138 to 116. So what happens is essentially as we bring those electrons in to make the double bond, kind of brings the atoms in closer. When we make a triple bond, kind of brings them in closer. So every time you kind of bring those electrons in to make an extra bond, it moves sort of everybody in closer to one another. And that has a big effect on bond strength. A triple bond is stronger than a double bond, and a double bond is stronger than a single bond. It's not like a triple bond is 3 times as strong as a single bond, but the general pattern is single bond is the weakest, triple bond is the strongest. Kind of like you have a brand new pencil, right? You could take it and pretty much snap it, no problem. If you take your pencil after a couple of chemistry exams, you're left with a nubbin and an eraser, right? It's like that big, very hard to try to break in half. And same idea, by bringing everybody in closer to each other, they're being held a lot tighter, making it a lot stronger of a bond that you have to try to break. So as we just talked about, though, with resonance structures, again, these are structures that really do develop because of those delocalized sort of double bond electrons. And it again means that, you can draw equivalent sort of Lewis structures for things where you do have options as to where to lay up that double bond. So once again, like our SO2 we just drew, we could have double bonded there to the right. And obviously here, we could have double bonded there to the left, which would not be that, it would be this. And as I mentioned before, you don't necessarily have to draw resonance structures on everything unless you're asked to do so. And again, if you're just asked to draw a Lewis structure, either one of these two obviously would be sufficient to draw. So here's another example. That's our ozone. Looks just like SO2. And again, double bonded on the left, or double bonded on the right. And our carbonate there that we just saw there, we could draw 3 different resonance structures for it with the double bond in different locations. Benzene is an organic compound that has 6 carbons and 3 double bonds. So you could draw some benzene structures that look like this. Basically, all these guys are carbons. And each of those carbons have a hydrogen attached to it, basically. It's an organic molecule. If you take organic chemistry, you'll get used to drawing it. But sometimes you'll actually see it actually just drawn with like a little circle in the middle. And that's to indicate that those double bond electrons are moving around. So the double bond could kind of be on either way there on the left or the right-hand side. It happens a lot. We'll skip this guy. So let's talk a little bit about the octet rule and actually some exceptions to the octet rule. Although in this class, we won't draw really any exceptions to the octet rule, you are responsible to know what the exceptions are. And once again, we won't draw any here, but when you go to 1A, you'll draw a bunch of exceptions to the octet rule. So we're just going to talk a little bit about what they are. The first exception to the octet rule is an incomplete octet. So much like the name implies, it is something that is perfectly fine with less than 8 electrons around it. For the most part, beryllium, not beryllium, well, beryllium and aluminum, but really the one that we come across the most is boron, the other B. Boron is really the one that we see the most in terms of an incomplete octet. Beryllium and aluminum are kind of metals, so not really involved a lot of times in obviously covalent bonding. So boron is typically the one you see there. Boron is sometimes referred to as being electron deficient, as it has less than 8 electrons. So as you can see there with BF3, boron is perfectly fine with just 6 electrons, and it doesn't need to make double bonds or triple bonds to fix it. It is an element that is okay with less than 8 electrons around it. And like I said, boron is probably the typical one that you see most of the time for that exception. Another exception to the octet rule is an odd electron molecule. That basically means when you add up all your electrons, you got one extra electron. So you have an unpaired electron. Those are sometimes referred to as free radicals. They're very, very reactive because they have just one electron. They don't really like to be that way. A lot of atmospheric chemistry involves chlorine that has a lot of unpaired electrons like that. And they're very, very reactive because of that. So another exception to the octet rule, which again, we will not see in here for the most part, is an odd electron molecule. The last exception to the octet rule is what's referred to as the expanded octet. And that exception is something that you will see a lot in 1A. So in 1A, that's all you see a lot of times is the expanded octet that you draw a lot. The expanded octet, again, like the name implies, is something that is okay going more than 8 electrons around it, upwards of like 12 electrons, 6 electron pairs. And it happens with elements on the periodic table around sulfur to the right, to the left, and down. That's because sulfur is on period number 3, which means N is equal to 3. And like we were talking about with electron configuration, on the 3rd energy level, we have what orbitals? S's, P's, and that's where we first start to see d orbitals. So those guys there actually have d orbitals available to them, although they may not be able to use them or use them. So they have an extra place to sort of stash the electrons. They can stash them in those d orbitals there. That also means that if you look at the periodic table for something like carbon, nitrogen, oxygen, that is period 2 on the periodic table, which is N equals 2, which has S and P orbitals only. Those guys should never, ever, ever go over 8 because they do not have the d orbitals available for them to do so. So they should always obey the octet rule. And here we should always obey the octet rule. But when you get to 1A, you'll go over 8 a lot with these incomplete, these expanded octets. Now, something like SF6 there, if we just quickly sketched it, basically looks something like this. I won't draw all the electrons on the fluorines, but they all have their dots. But essentially, we got 1, 2, 3, 4, 5, and 6 electron pairs around the sulfur, which is a total of 12 electrons, and it's perfectly fine and able to do that because of the d electrons, the d orbitals are there. That's also why if you look up something like sulfate, for example, online, You will see it perhaps drawn like you would get if you followed our pathway here, all single bonded. But you may see the structure drawn with some double bonded oxygens. And that is an acceptable structure for sulfate, and it's able to do that because the sulfur can go over 8 electrons. Actually, in this case, the double bonded one is the better structure of the two, and the single bonded one is actually not the better structure, but it's able to do that. And we'll talk about what's known as formal charge when you go into 1A as well, and that's why it's a better structure on the right than the left. But for us, you should really end up with the guy on the left because we'll obey the octet rule. But in reality, again, things can definitely go more than 8. So incomplete octet, odd number of electrons, and expanded octet are 3 exceptions to the octet rule. And once again, here we will again obey the octet rule. Any questions on those there? So we're talking a little bit about molecular geometry here. And we could kind of look at our Lewis structure and really the central atom when we are doing geometry. And when we do geometry, it really is always the center atom that's the most important. So you always want to look at the guy in the center when you're doing geometry. And we're going to talk about 2 types of names in terms of geometry. One is what is referred to as the electron pair geometry. Which I'll just abbreviate as EG. And that describes the 3-dimensional arrangement of the electron pairs around the central atom. And the other one is the molecular geometry. I'll abbreviate that as MG. And that is also sometimes referred to as the shape. And that's the overall shape of the molecule based on really what type of electrons there are around the central atom and how many bonds you got going on. As we will see, in certain cases, those names are the same, and in other cases, they actually do differ depending, again, really on the type of electrons that we got going on there on the central atom. Now, in most cases, a lot of things that you draw will have just one central atom, but if it does have multiple central atoms, you just do the geometry for each one separately. So if you have multiple central atoms, you do each central atom individually for the geometry. The idea here is obviously electrons are involved. Electrons are negatively charged, which means ultimately electrons do not want to be near each other. So what happens is they can't really escape, but what they can do is try to get as far away as possible from one another. And what that ends up doing is really changing sort of the shape sometimes of the molecule as they move. Remember that as electron pairs move, if they're attached to atoms, they're going to move accordingly, right? And the whole thing will kind of shift as the electrons ultimately are trying to escape one another, basically. So this is what is known as VSEPR, valence-shell electron pair repulsion model, hence the abbreviation. And it basically is divided into 2 types of categories. One where we have no lone pairs on the central atom, so basically no dots on the central atom when you draw your Lewis structure, and one where we do have dots. Our lone pairs there when you draw it. For the most part, the most important thing when you're doing geometry, or one of the most important thing, is what it says there at number 1, which is if you have a double bond or you have a triple bond, you should count it as only 1 electron pair and 1 bond. So effectively is moving as 1 unit. So it counts as only 1 electron pair and 1 bond. Double bond, triple bond, single bond, doesn't really matter when you're doing geometry. It's always 1 electron pair and 1 bond. So let's talk about really the simplest ones that you could have. And those are diatomic molecules. So if you got like H2, F2, O2, HF, HCl, N2, Now, it doesn't matter in any of these cases if it's single bonded, double bonded, triple bonded. Frankly, there's just two atoms involved. And the old saying is, right, the shortest distance between 2 points is a straight line. So that is basically always going to be the geometry for anything that's diatomic. They will always have a geometry basically of linear of each other, basically a straight line from one to the next. There is no central atom here, so there really is no bond angle or anything like that because you need 3 to have a bond angle. So here it'll always be linear again, no matter single bonded, double bonded, triple bonded, no matter if it's 2 of the same elements, 2 different elements, put linear, move on with your life. It'll be okay at that point. Yeah. Now, if everything was that simple, it would be great, but obviously it's not. So let's talk about some examples where we do have 3 or more atoms involved. Geometry for most people is a memorization thing. Yeah, most people cannot visualize 3-dimensional space, myself included. So the best way to do it is to sort of make a chart. And what we really want to look at is usually the number of electron pairs around the central atom. So once again, it's always the guy in the middle that's most important. And we're really looking at the number of bonds. So you might want to make a little chart as we go through this, but this is the best way to sort of do it. So when we look at the central atom, again, it doesn't matter if they're lines or dots, the total number of electron pairs in this particular example is 2. And the number of electron pairs determines the electron pair geometry name. And something with 2 electron pairs is also linear of each other. Now, what's going to happen is basically those electron pairs are going to decide, let's go away from each other as far as possible, which is basically on opposite sides of each other. And what we end up with is something with 2 bonds. So something with 2 electron pairs and 2 bonds, the molecular geometry or the shape would also be linear. So once again, they're bonding electrons. So those 2 atoms are just going to go away as far as possible, basically on opposite sides of each other. And we end up with a bond angle of 180 degrees in this case. So 2 electron pairs and 2 bonds, the electron pair geometry is linear, and so is the molecular geometry name. The next sort of geometry is one where we have 3 things bonded to the central atom. So here, if we look, number of electron pairs, and once again, it is the center atom that's most important. This guy has 3 electron pairs, 1, 2, and 3. And number of bonds also going to be 3, 1, 2, and 3 bonds. Something with 3 electron pairs, what happens in this case, the electron pair geometry name is going to be trigonal planar, or sometimes referred to as triangular. Basically, what happens is now we have an extra bond in there. So this guy is like, well, we got to go away from the guy at the top. The guy at the top's going, we got to go away from it. And what ends up happening is we get a molecular geometry shape of also trigonal planar. And that's because it frankly makes a triangle shape. Basically, what happens as they kind of spread out from each other makes an equilateral triangle with a bond angle of 120 degrees that happens. So again, with that extra bond that's there, they can only go so far away from each other. Yeah. So electron pair geometry describes in 3-dimensional space how the electron pairs are kind of distributed in 3-dimensional space. The molecular geometry name describes what the overall molecule's overall shape is. At this point, they're both the same. We're going to get into a couple of cases where they're not going to be the same. And they're both the same in this case, really, because the only type of electrons we have here are bonding electrons. So all the electron pairs are tied to an atom. So as those electron pairs move, so do the atom, which means the overall shape and how the electron pairs kind of move are all going to be the same because they're all attached to it. And it's because they're all bonding electrons. Other questions? Okay. The next example here will be one where we have 4 things attached there to the central atom. So if we look at the number of electron pairs around the central atom, we got 1, 2, 3, and 4. Number of bonds here going to also be 4, as those are all bonds as well. And something with 4 electron pairs, electron geometry name is going to be tetrahedral. Now, in this case, we don't have 3 bonds, but now we got 4 bonds, which means as like these hydrogens sort of move away, so as these guys try to move away from each other, and we end up getting a molecular geometry name of tetrahedral as well, which is kind of like a triangle on the outside, almost pyramidal on the bottom, sort of geometry that sort of happens in this case. Once again, both of these names just like the first 3 that we talked about, because again, in this case, the only type of electrons around the central atom are bonding electrons. And as those bonding electrons move, so does the atoms, and the overall shape of the molecule again ends up being exactly the same sort of shape as the electron pair geometry. So whenever you draw your Lewis structure and you have no dots on the central atom, so no non-bonding electrons, both the electron pair geometry name and the molecular geometry name will always be the same because they're bonding electrons. What happens and when they start being different is when we introduce non-bonding electrons. So what happens when we introduce non-bonding electrons into the mix is, instead of something where we have bonds all the way around, for example, we now have something where there is no atom attached to it. And that gives those non-bonding electrons a little bit more freedom to move, and also allows them to get away from the bonding electrons a little bit more. And what ends up happening is the overall shape, the molecular geometry shape, actually starts to change a little bit more because there's a little bit more freedom there without that extra atom attached, that they're able to kind of escape a little bit more. And what we start to see is it is the molecular geometry name that actually changes. The electron pair geometry stays the same because there's still, for example, 4 electron pairs around the central atom or whatever it may be. But as they sort of move around without those extra bonds in there and just the non-bonding electrons, it allows the molecular geometry to change a little bit. The other aspect of this is because really what's happening is we start to get some different electron-electron interaction that occurs. So everything that we just talked about, where both names are the same, that's all bonding versus bonding, which means lines near lines. And that is basically electron-electron interaction that could happen. They're not happy to be there, but they're not so unhappy that they're going to run for the hills as far as they can. The next worst interaction is when you get lone pair near bonding, so dots near lines. So when you draw a Lewis structure that has dots near lines, basically those 2 things do not want to be near each other. And because the non-bonding electrons are not tied to another atom in a bond, it has a little bit more flexibility and movement that could happen. And that affects the overall geometry of the molecule. The worst interaction that you could have is non-bonding near non-bonding. So when you draw a Lewis structure and you got dots near dots, those 2 do not want to be anywhere near each other. So those 2 try to run for the hills as far as possible. As they're moving away from each other, everything else is basically attached. So they got to kind of move with them. So they try to get away until they come to rest at a sort of an acceptable distance from each other in each of these cases. Let's look at one here. This occur. This is our sulfur dioxide. So we drew that earlier. Let's just resketch it real quick. So if we look at the number of electron pairs here around the sulfur, in this case, we have 1 electron pair, 2 electron pairs, and our double bond counts as only 1 electron pair. So this is a grand total of 3 electron pairs in this case. The number of bonds in this case would be only 2 bonds in this case. And once again, it would be 1 bond here. And again, the double bond would count as only 1 bond. So important when you're doing geometry, double bond, triple bond, only 1 bond and 1 electron pair. As I mentioned before, because it still has the 3 electron pairs around it, these electron pairs are going to get out into that trigonal planar 3 geometry sort of name. But because this guy here is no longer attached to a bond, like it is in a traditional trigonal planar where it makes like a nice equilateral triangle with that bond going upwards, it has a lot more movement that it can stretch out. And it ends up being a molecular geometry known as angular. Now, some people call it angular. Some people call this one straight up bent. Some people call this bent angular. We are going to, for lecture here, use angular for this arrangement of 3 electron pairs and 3 bonds. And that is because the bond angle here is less than 120 degrees. Again, because of this non-bonding electron, is not going to be as sharp of a triangle sort of angle, and there's a little bit more room of movement because there is not that 3rd bond that is there. Any question on that one here? So once again, it is the molecular geometry name that changes. Electron pair geometry stays the same. We look at next NH3. NH3 here, looking at the nitrogen in the center. Number of electron pairs has 4. 1, 2, 3, and 4. Again, doesn't matter if they're dots, doesn't matter if they're lines. Number of bonds in this case will just be 3 in this case. So something with 4 electron pairs in terms of the electron geometry is going to still be tetrahedral. Same thing happens here. We have these 3 hydrogens that want to kind of escape each other. And we got the non-bonding electrons that definitely want to get away from each other. And what ends up happening is we end up with this shape that is known as trigonal pyramid. And that is because it's got these non-bonding electrons, kind of makes a triangle and a pyramidal shape there on the bottom that basically occurs. Bond angle here is based off of the electron pair geometry. So the bond angle is less than 109.5, about 107 in this case, give or take. So once again, we see the molecular geometry name change as we incur some non-bonding electrons. We have 2 types of interactions happening here. We have bonding electrons near bonding. Then we also have non-bonding electrons near bonding. Again, that non-bonding versus bonding electrons going to try to get away a little bit further, and that's causing the overall shape of the molecule basically to change. This is a good time to talk about a couple of names we've talked about up to this point. We did trigonal pyramid here. Earlier, we did trigonal planar. There are 2 different things, these 2. So on a test, you should not just write trigonal and let me choose, because I failed chemistry, so I will choose wrong. So don't let me choose. Do not write trigonal. Clearly that is pyramid or planar, depending on which one it was. Yes, so you need to make a clear choice, and they are different. One is a bond angle of 120, one's a bond angle about like 107 basically, so they are different in terms of their shapes. Last sort of geometry that you need to know is something that we see like in water here. And when we look at water, the number of electron pairs around the central atom here is going to be 1, 2, 3, and 4. The number of bonds is going to be 2 in this case, 1 and 2. Something with 4 electron pairs, the electron pair geometry is going to be tetrahedral. In this case, we have pretty much all the interactions happening. We have bonding electrons near bonding. We have non-bonding electrons near bonding, and the worst interaction you could have, which is non-bonding electrons near non-bonding electrons. So what ends up happening is, in this particular case, the non-bonding electrons try to go this way and this way, kind of away from each other. The result of that is the hydrogens has to basically come down away from each other because they also want to keep a distance. And we end up with this shape, which is known as bent or V-shaped. So the shape here for molecular geometry is bent or V-shaped. It has a bond angle of less than 109.5. It's about 104 in this case. And that's why you see water is sort of drawn in that way, because of those non-bonding electrons trying to escape each other, causing the hydrogens really to come away from those guys as far as possible. But again, they can't fully escape, so they got to lock into place at some point, energy-wise and stability-wise, that is sort of acceptable. Any questions on that there? Best way to do it is number of electron pairs, number of bonds, and have a list to memorize it. Up on our Canvas side where the lecture notes are, there's a little table I made of all the geometries and number of electron pairs, number of bonds, along with molecular polarity, which we're going to talk about here in a second. So it's a good thing to look at. It's the best way to kind of do it. Yeah. Any questions on that? So you do need to obviously be able to draw a Lewis structure, be able to identify the electron pair geometry name and the molecular geometry name as well. Here's a table from your book, similar one that has all that. The last thing we're going to talk about here in terms of bonding is molecular polarity. And when we talk about molecular polarity, we're talking about the entire molecule as a whole. Is the molecule sharing electrons equally or unequally here? And if something is a polar molecule, it will have what is referred to as a dipole moment if it's a polar molecule. And we oftentimes will represent it with that dipole arrow we use for bond dipoles, where it points to the more negative side, this guy to the more positive side. If it is a non-polar molecule, it means it will not have a dipole moment. It's essentially neutral. So if you have a polar molecule, basically what that means is overall, there's a side that's more positive and there's a side that's more negative as a result of unequal sharing of electrons over the entire molecule, if this is a polar molecule. If you have a non-polar molecule, maybe not the best description, but it's kind of neutral. So there is no side of the molecule that's more positive. There's no side that's more negative, because there's an even distribution of electrons over the entire sort of molecule, if you will. Now, the most simplest ones to figure out whether or not the molecule is going to be polar or non-polar are diatomic molecules. And that is because diatomic molecules, frankly, only have one bond. So it makes it really simple. So if you have a diatomic molecule, say like H2, like F2, we'll draw the dots, O2, and so forth. All of these bonds here, right? These are all diatomic. We could use electronegativity values to help us decide if it's polar or non-polar. The F2 bond here, that would be polar or non-polar. That would be 4 and 4. 4 minus 4 is equal to 0, which means it is a non-polar bond. So is the oxygen here, so is the hydrogen, because they're both the same element. They both will have the same electronegativity value that will always give you a 0, which means it should always be non-polar. So each of these guys up here have only one non-polar bond. And because these guys are diatomic, that is the only bond in the entire molecule, which means because the only bond in the entire thing is non-polar, these guys have to be non-polar molecules. Which means overall, they're sharing the electrons equally. We have something like HF, HCl, These are polar bonds, right? For the more electronegative here, for example, the fluorine, we would draw the arrow heading towards the fluorine. And because in each of these cases, that is the only bond in the entire molecule, the molecule also has to be polar as well. Be polar. And this would be our dipole moment drawn towards the fluorine. So diatomic molecules are super easy because they only have one bond. All you have to do is figure out, is that bond polar or non-polar? And that will also tell you the molecular polarity. That is the only place where molecular polarity and bond polarity, where we use electronegativity values, that's the only place where they both are the same. Yeah, they kind of cross over. They're basically the same thing. When you have 3 or more atoms involved, it'd be nice if it was this simple, but it's not. So when you have 3 or more atoms involved, you actually have to look at 2 things to determine whether or not this molecule is going to be polar or non-polar. So when you have 3 or more atoms, you need to look at, are there polar bonds? So obviously, if the answer is no, there's no polar bonds, then probably the molecule is going to be non-polar at that point. If the answer is yes, there are polar bonds, you then need to look at the molecular geometry or the shape, or as we were just writing at the MG, basically. Yeah. So you have to look at the molecular geometry here. So for example, if we look at something like CO2, and if we draw something like CO2, the bond between carbon and oxygen, is it polar or non-polar? It is polar. We know that without even needing the numbers, because carbon and oxygen are the same row on the periodic table, and oxygen is further to the right, which means it should be more electronegative. So we could draw our bond dipoles heading towards the oxygen here. And this would have polar bonds. Now you may think, well, it has polar bonds, so that looks good for it being molecular polar. We do have to look at the geometry here. So the molecular geometry here is, this guy has 2 electron pairs and 2 bonds. Something with 2 electron pairs and 2 bonds, the geometry is linear, right? So what we have in this particular case is a linear geometry like my pen. We have oxygen pulling to the right. We have oxygen pulling to the left. I'm pulling on both of my pins here on both sides. My pin is going nowhere. Yeah. So although it does have polar bonds, because of the geometry, this thing is actually going to be a non-polar molecule, which is a very good example of something that can have polar bonds, but overall be non-polar. And that is because these little things here, these bond dipole arrows, these are what they call vectors, I think, in physics, right? They have direction, they have magnitude. Then I fell asleep. But then I woke up long enough to know in certain cases they cancel each other out, right? And in other cases they actually add to each other. Cases where they cancel each other out is like when they're going equal and opposite of each other, like in this case, like pulling on a rope. Or if they're like heading like right at each other, like if you had a swinging door and 2 people on opposite sides pushing equally, right? The door is not going to go anywhere. They're going to cancel each other out. So anytime these guys basically towards each other, equal and opposite, or opposites of each other and equal and opposites, they actually cancel each other out and will result in a non-polar sort of situation. If we look at something like water, which is a polar molecule, and we'll see why that is here. When we look at water, the bond between hydrogen and oxygen is polar as well, with oxygen being more electronegative, heading that way, heading that way. So once again here, we do have polar bonds. The geometry here is, when we look at the central atom like we saw, it has 4 electron pairs. And it has 2 bonds. And that is our bent, our V-shaped geometry. So in this case, instead of the linear geometry, we got kind of like a V happening where we got this guy coming up this way. You can almost imagine like a string on top, and you pull it, the whole thing will sort of move. And this guy would be a polar molecule, because in this particular case, those vectors are actually going to add to each other and give you what is referred to as a net dipole moment heading in this direction, where the oxygen part of water is more negative, the hydrogen part of water is more positive, and that would be our dipole moment, which looks exactly like our bond dipole arrows because it is the same arrow basically used for both things. So in case you're curious, I think I woke up long enough to see that you do this going in that direction, then you're going to go head to tail, right? And then these guys add to each other heading in that direction is sort of how the vectors work there. Nobody wants to do vectors because I don't want to do vectors. So why would you want to do vectors, right? So there are certain ways that you can kind of quickly and probably in most cases have the right answer. And that is based on the geometry. And there are certain geometries which are sometimes referred to as being symmetrical geometries. And for you guys, symmetrical geometries would be trigonal planar or tetrahedral. And what we're talking about here is the molecular geometries here. What all these two have in common is when you draw your Lewis structure, you have no lone pairs or dots on the central atom. And if you have no lone pairs on the central atom and everything, all the outside atoms are the same element, this will result usually in a nonpolar molecule. So if you take something like CF4 here, I won't draw the dots on the fluorine, but between carbon and fluorine, basically we do have polar bonds happening, all heading towards the fluorine. But really, if we look at this, my central atom has no dots. Everything on the outside is exactly the same, which means this would be a nonpolar molecule. Now, what would happen if I take my same guy basically, but instead of the 4 fluorines, I swap one out for hydrogen? In this particular case, we would still have our polar bonds heading here. The carbon-hydrogen bond, polar or nonpolar? It is actually nonpolar. It's a 0.4 difference we did. So it's like at the edge of being nonpolar. So what we have in this case is, for lack of 3D drawing, we got these 3 guys kind of pulling and the guy in the back not really doing much, right? So you can imagine if they did that, nobody would going back the other way, the whole thing would move. Actually, this guy is actually heading a little bit towards the carbon as well. So he's actually going with them. So the whole thing would move, and then it would become actually a polar molecule in this case. So here's the deal. If you draw your Lewis structure, you have no dots on the central. It's exactly the same element, right? Nonpolar molecule. You'll be fine. If you draw your Lewis structure, there's no dots on the central atom, and all the outside atoms are not the same. There's at least one that's different. It's probably going to be a polar molecule. It'll go from nonpolar to polar in that case. Any questions on that there? Now, there are some unsymmetrical geometries. And for you guys, that would be angular. That would be our trigonal pyramid. And that would be our bent, our V-shaped. And basically what all these have in common is when you draw your Lewis structure, you got non-bonding electrons. On the central atom, you basically got dots. Yeah. And if you have that situation and all the outside atoms are the same, it is going to be a polar molecule. So that's a pretty safe bet. That's how we get to water, for example. I draw water. I see dots on the central atom. I see everybody on the outside is the same. I say it's polar. Yeah. So that's a really good way to do that. So let's take a look at some maybe that we've seen. Let's do this here. Let's do this. Let us do this. Let's do this guy here. And let us do this guy here. All right, so this is how quick you could do it, and you'll probably be right most of the time. I look at the central atom. I see dots. I see everybody the same on the outside, polar or nonpolar. Polar. I look at the central atom. I see dots. Everybody on the outside the same, polar or nonpolar. I see no dots. Everybody on the outside is the same, polar or nonpolar. I see no dots. Everybody on the outside is the same, polar or nonpolar. Nonpolar, yeah. Doesn't matter, double bond, doesn't matter any of that thing. No dots, everybody on the outside is the same, nonpolar. How about this one? I see no dots, everybody on the outside is not the same, it's going to be polar, yeah. There you go. Any questions on molecular polarity? That's probably the best way. What that really does leave you though is just linear, which is a straight line. So that one's pretty easy to figure out. If it's like CO2 where they go opposite of each other, it's going to be nonpolar. If it's like two that are kind of going towards each other in a linear fashion, it's going to be nonpolar. But you could have one that's linear where everybody's heading in the same direction in terms of electronegativity, then it would be a polar molecule. So that one's not too hard to sort of figure out. But everybody else, not too bad. So, if you had something like this would be polar or nonpolar. By the way, let's start with this. What is the geometry of this guy? Molecular geometry. It is linear, 1 electron pair. This counts as only 1, and each one counts as a bond. So that's 2 electron pairs and 2 bonds. This is linear. Between carbon and nitrogen is more electronegative, right? And carbon and hydrogen is nonpolar, which means the only thing we got going on in a linear fashion is somebody heading in this direction. So if you thought about like a rope and somebody just pulled one side of the rope, right, it's going to go, right? So it's going to move. So it would be a polar molecule in this particular case. Question on molecular polarity there. Question on bonding or any of that type of stuff there. All right, that wraps up that chapter there on bonding. Not too bad. This for our last little bit here. Okay, so this is chapter 5. This is nomenclature, which is naming, and we're going to talk about 2 different types of naming. Obviously, from our bonding, we're going to talk about ionic, which is always our metal and non-metal together, where our metal is going to transfer electrons and again result in a cation that's positively charged and our anion that is negatively charged. The other type of naming is ones that involve covalent bonding, or they're sometimes referred to as molecular. And in this case, it's usually 2 nonmetals, and it's some aspect of sharing of electrons, as we talked about there in bonding. And what combination you got going on there, ionic or molecular, you do name them differently depending on sort of the type of compound that you're dealing with. So there are a few things that we just go by common names, and I would say these 3 here are really the most important ones. H2O is water. It's not a trick question. It is water. It's not dihydrogen monoxide. Nobody wants a refreshing glass of dihydrogen monoxide. They much rather have water, I imagine. NH3, which is ammonia, not to be confused with the polyatomic ion that we will see that looks very much like it. NH4, which is ammonium. CH4, like what comes out of our Bunsen burner vent there, is methane. That's the simplest organic molecule you could have. I'll be honest with you, most people still call this sodium chloride, not really table salt. So most people call it sodium chloride and sugar. So those 3 in the box for sure. You should definitely always go by the common name when you have those 2. So let's talk a little bit about compounds, our naming of compounds here. Binary compounds, which are composed of 2 or more 2 elements, again, are our nonmetal and metal together, which is ionic. and our two nonmetals, which is molecular, are covalent. So we're going to start with ionic here. And ionic really can be broken up into sort of two categories, type 1 or type 2 compounds. Type 1 or type 2 compounds are always ionic. They're always the metal and the nonmetal. And always when you have a metal and nonmetal together, it's always the metal that is most important. But let's talk a little bit about sort of what we get here in terms of our ions. We do get from the metal a cation, which is positively charged, and that does come from the metal. And from the nonmetal, we do get the anion, which is negatively charged. Now, if we have a metal that's a cation like H plus or Ca2 plus or Na plus, we simply just use the whole name of the element. So this would be the hydrogen ion. This would be the calcium ion. This would be the sodium ion. These are all formulas for cations. So if you're ever asked to write the formula for the cation, it should always have the charge. So anytime you write a formula for an ion, because it's an ion, it should always have a charge. So you should always include the charges for those guys. On the negative side, you could have something like H minus, maybe Cl minus, maybe O2 minus. The negative guys, the nonmetals, we drop the last part of the name and we add IDE to it. So hydrogen would become the hydride ion. Cl is chlorine, would become the chloride IDE ion. And oxygen would become the oxide ion. So negative guys get the IDE ending. Positive guys just use the whole name of the element. Hydrogen is the only one that could kind of go both ways. It could be positive in certain cases and negative in others. For the most part, hydrogen will most likely be positive. Hydrogen is only negative when it comes after a metal. So if metal then is going to be negative. Otherwise, hydrogen in most cases will be positive in terms of you name it. This is also related to the charges that we see on the periodic table. I think we talked about them, but just to make sure one more time here. When we look at the periodic table, right, everybody in group 1 makes a +1 charge. Everybody in group 2 makes a +2 charge. We'll go to group 3, 4, 5, 6, 7, and 8. All right, so that's really bad drawing there, huh? So 4, 5, 6, 7, and 8. This is why I did not take art. All right, let's try that again there. Maybe one more line at work. All right, we'll just add one at the end here. Now we got 3, 4, 5, 6, 7, and 8. There we go. All right, and group 3, it's usually aluminum that we're talking about here. It's going to be +3. This is where our staircase kind of comes in. Starting at group 5, it's -3, -2, and -1. -1 there. And that's for our nonmetals, right, above the staircase. These are our transition metals, and they could have multiple charges. And there are 3 exceptions, though. That is zinc and cadmium will always be +2. And if you hang over there to silver, that will always be +1. So those are 3 exceptions in the transition metal region. Everybody else will have variable charges, including some of these guys down in here where lead and tin and all those guys, they also will have variable charges. So that's obviously a good thing to remember here. Okay. So in addition to these ions, when we write the formulas for these guys individually, whenever we take a positive ion and a negative ion and put it together, should always equal 0. So if we had, like we talked about in bonding, a calcium and a F, we always want to put them together to equal 0. And that means we would need 2 of the F minuses. That gives us a -2 to balance out the +2. And the proper formula here would be CaF2. So whenever we write the formula for an ionic compound, when we put them together, the guy and negative guy should always equal 0, should have no charge, but it is made up of, as you can see here, 3 things with charges. So it is made up of ions, but we never ever have charge when we put the negative and positive guy together. It needs to equal 0 in the simplest way possible. The reason for that is what we talked about with bonding. That is, if you remember, what allows everybody to get to the noble gas configuration. So if you remember, calcium had 2 electrons to get rid of. It can only get rid of 1 electron to 1 fluorine. So it needed that extra fluorine to take the second electron. And that is, again, really the reason why when we put them together, we get everybody to that 0 spot. Any questions on that there? All right, we will lay it up there for today. Finish our